Every single second, Netflix is processing over 8 million requests. Requests to start videos, requests to update watch history, requests to generate personalized recommendations, requests to track exactly where you paused, all happening simultaneously on the same platform across 190 countries. Now, here's the question every distributed systems engineer eventually has to answer. How do you design a database layer that handles reads at 8 million requests per second without destroying your write performance? The answer Netflix landed on is a design pattern called CQRS. And in this video, I am going to show you exactly how it works, why Netflix needed it, and what it looks like inside a real production system. The scale problem that created CQRS. Let me start with the fundamental problem that CQRS was designed to solve. In a traditional architecture, you have one database model, one table structure, one set of indexes, and you use that same model for both reading data and writing data. At small scale, this is completely fine. When you have 10,000 users, your database handles both reads and writes without any friction. But now let me show you what happens at Netflix scale. Netflix serves over 230 million subscribers. At peak hours, their streaming platform accounts for approximately 15% of all global internet traffic. Think about what that actually means. 15% of everything moving across the internet at peak time is Netflix. In that environment, reads and writes have completely different characteristics. Reads are enormous in volume. When someone opens Netflix, the platform is reading your personalized home screen, your viewing history, your saved titles, your recommendation scores, your device capabilities, and your geographic licensing rules. That is potentially 20 to 30 separate read operations happening before a single frame of video plays. Writes are much lower in volume, but they are extremely time sensitive. When you start a video, Netflix writes a playback event. When you pause, it writes a position update. When you finish an episode, it writes a completion event and triggers a recommendation update. These writes need to be fast and they need to be durable. If that write is lost, Netflix does not know where you stopped watching. So here is the collision. Reads and writes have completely different performance requirements. They need different indexes, they often need different data structures entirely. Trying to satisfy both use cases with a single database model is exactly where performance collapses at distributed systems scale. This is the core problem the CQRS design pattern in microservices was built to solve. What CQRS actually is. CQRS stands for Command Query Responsibility Segregation. Let me break that down precisely. The core principle is this. You separate the part of your system that handles writes, which are called commands, from the part that handles reads, which are called queries. In a traditional architecture, one model serves both purposes. In a CQRS pattern, you have two completely independent models. The command side handles everything that changes state. Creating a user account is a command. Updating a watch position is a command. Recording a rating is a command. Adding a title to your list is a command. These operations write to a write database that is optimized for fast, durable, transactional writes. The query side handles everything that reads state. Fetching your home screen is a query. Loading your watch history is a query. Getting your recommendation feed is a query. These operations read from a read database that is optimized specifically for fast reads at high concurrency. Now here is the insight that makes this architecture so powerful. The write database and the read database are not the same database. They do not need to use the same technology. They do not need to store data in the same format. They are completely separate systems, each optimized independently for their specific job. The write database might be a normalized relational schema optimized for transactional integrity and write throughput. The read database might be a fully denormalized document store or a distributed cache optimized for sub-millisecond reads at massive parallel scale. Between the two sides, there is a synchronization mechanism. When a command writes to the write database, that change is propagated to the read database through an event stream. That propagation is asynchronous. It does not need to happen instantly. It needs to happen reliably and in order. The single most important thing to understand about this diagram is that arrows only go in one direction. Commands flow from the application to the write database. Events flow from the write database to the read database. Queries read from the read database only. The query side never touches the write database. This separation is what allows the system to scale each side independently. Event sourcing plus CQRS. Now let me talk about the mechanism that connects the two sides. Event sourcing. In a traditional system, when you update a record, you overwrite the old value. The previous state is gone. You store the current state and nothing else. Event sourcing takes a completely different approach. Instead of storing the current state, you store a log of every event that led to the current state. Think of it like your bank account. A traditional database would store your current balance as a single number. Event sourcing would store every deposit and every withdrawal as separate immutable events. Your balance is not stored directly. It is computed by replaying all the events in sequence. For Netflix, this means every user action is stored as an immutable event record. User started video at timestamp T, user paused at position 38 minutes and 22 seconds, user rated title 4 stars, user added title to their list. User resumed from last position. That event log is the write database. It is the source of truth. It is append only. Nothing is ever overwritten. Nothing is ever deleted. The read database is then built by consuming those events and projecting them into whatever data shape is most useful for each specific read use case. You can build multiple, completely different read projections from the exact same event log. One projection for the home screen personalization, one projection for the recommendation engine, one projection for the analytics and reporting pipeline, all derived from the same underlying events. And here is the operational superpower of CQRS event sourcing working together. If your read projection gets corrupted, or if you want to rebuild it in a new data format, you do not need a backup restore. You replay the event log from the beginning and rebuild the projection completely fresh. The source of truth is always the event log. How Netflix actually uses this in production. Now, let me get specific about how Netflix applies this architecture in production. Netflix does not have one CQRS system. They have dozens of independent instances of this pattern, each handling a different domain of their platform. Let me walk you through the three most critical ones. The viewing activity service. Every time you watch something on Netflix, the platform needs to track precisely what you watched and how far you progressed. This is critical for two reasons. First, it needs to remember your exact position, so you can resume from where you stopped. Second, it feeds the recommendation engine that decides what to surface for you next. The right side of this service receives playback position events at high frequency. Position updates arrive roughly every 30 to 60 seconds while you are actively watching. Across tens of millions of concurrent viewers at peak hours, the write volume is extraordinary. The read side needs to serve your complete viewing history to the recommendation engine, to your profile overview page, and to the continue watching row on your home screen. Each of those three read use cases needs different data in different shapes with different latency requirements. By separating these concerns through the CQRS pattern, Netflix scales the read side completely independently from the write side. When recommendation queries spike, they provision more read replicas without touching the write pipeline. When playback event writes spike, they scale the write infrastructure without affecting the read path. The two operations never contend with each other. The recommendation engine. Netflix's recommendation system is one of the most complex read workloads in existence. When you land on your home screen, Netflix is computing a personalized ranking across thousands of potential titles, applying geographic content licensing rules, checking real-time content availability, scoring your engagement patterns, and assembling a structured response for your specific device profile. All of that needs to complete in under 200 milliseconds. This is a read-heavy workload with extremely aggressive latency requirements. By projecting the event log into pre-computed recommendation scores stored in a distributed cache, Netflix eliminates on-demand computation from the read path entirely. The query side returns pre-built personalization data that was computed asynchronously in the background. The read path is just a cache lookup. It is nearly instantaneous. This is the CQRS design pattern in microservices operating at its most powerful. The computational complexity is completely decoupled from the read latency. Your home screen loads in under 200 milliseconds, not because Netflix is computing recommendations that fast, but because the recommendations were already computed before you even opened the app. the streaming delivery pipeline and adaptive bitrate streaming. Netflix delivers video using adaptive bitrate streaming. The system continuously monitors your available network bandwidth and switches between different video quality levels to maintain smooth, uninterrupted playback. The command side records your current network conditions and playback state as events. The query side reads the appropriate bitrate profile for your current conditions and returns the correct stream segment. These two operations run on completely separate infrastructure. This is why Netflix can deliver 15% of global internet traffic. Each subsystem scales independently. Reads scale independently from writes. Event processing scales independently from event storage. The entire system grows horizontally in every dimension without any single bottleneck. The technology stack. Let me now cover the specific technologies Netflix uses to implement this architecture. For the event stream, Netflix uses Apache Kafka. Kafka is the asynchronous pipeline that carries events from the command side to the read side. It is distributed, it is durable, and it is architected specifically for extreme throughput. Netflix runs one of the largest Kafka deployments on the planet, processing trillions of events per day across their global infrastructure. For the write database, Netflix uses Apache Cassandra. Cassandra is purpose-built for fast, durable writes at distributed scale. It is eventually consistent by default, which fits perfectly with the CQRS model, because the write database does not need to serve reads directly. It only needs to accept writes quickly and propagate events reliably into Kafka. For the read database, Netflix uses a combination of Cassandra for persistent read models and Elasticache backed by Redis for low-latency hot reads. Pre-computed projections are stored in Redis, so the most frequently accessed read queries return in single-digit milliseconds. For event stream processing, Netflix uses Apache Flink. Flink reads from Kafka, processes the event stream in real time, and continuously updates the read projections in Cassandra and Redis. Flink is the synchronization engine between the command side and the query side. It is the system that keeps your read database current with minimal lag behind the write database. The entire pipeline runs on AWS and is managed through Netflix's internal container orchestration platform called Titus. Titus is built on top of Apache Mesos and is specifically designed for the unique characteristics of Netflix's distributed systems workloads. Trade-offs and when not to use CQRS. Now, I want to be completely transparent about the trade-offs. CQRS is a powerful pattern, but it is not the right choice for every situation. The biggest cost is eventual consistency. Because the read database is updated asynchronously, there is always a small window of time where a write has completed, but the read projection has not yet caught up. If you write something and immediately try to read it back, you might get stale data. For Netflix, this is an acceptable trade-off. If you rate a movie and your rating does not appear on your profile for 2 seconds, that is a minor inconvenience. If you add a title to your list and it does not appear in your list row immediately, you will not even notice. The user experience is not meaningfully degraded by this consistency lag. But for some systems, eventual consistency is completely unacceptable. A financial transaction system where a debit must immediately and accurately reflect your new available balance is not a good candidate for naive CQRS without very careful additional design around consistency. Guarantees. The second cost is operational complexity. You are now maintaining 2 separate data stores and a synchronization pipeline between them. That is additional infrastructure to build, monitor, operate, and debug. For a small engineering team or a low-traffic application, that overhead is almost never justified. The practical decision rule is straightforward. If your read and write workloads are already causing strain on a single database model, and if they have genuinely different scaling characteristics, CQRS is worth the investment. If you are running a startup at small scale with a simple data model, a traditional CRUD architecture will serve you better and ship faster. Let me bring everything together. CQRS is the pattern of separating read operations from write operations into completely independent models, each optimized for their specific job. Netflix applies this pattern across dozens of their microservices to solve the fundamental distributed systems problem of reads and writes having incompatible performance requirements at global scale. Event sourcing provides the synchronization mechanism. Every state change is stored as an immutable event. Read projections are built by consuming those events and transforming them into whatever data shape each query use case requires. The Netflix production stack uses Apache Kafka for event streaming, Apache Cassandra for durable storage on both sides, Redis and Elasticache for low latency read cache, and Apache Flink for real-time event stream processing. The trade-offs are real and they matter. Eventual consistency and operational complexity are the costs. At Netflix scale, those costs are absolutely justified by the independent scalability gains. At small scale, they may not be. In the next video, I am going to go deeper into event sourcing as a standalone pattern and show you a complete implementation of event sourcing with projection rebuilding on a Postgres backend. If you are building distributed systems and you want to see that implementation end-to-end, subscribe right now because that video is coming out this week. If you are working on a real system design challenge right now and you are trying to decide whether CQRS is the right fit for your architecture, drop the details in the comments below. I read every comment and I use them to build exactly the content this community needs.